In the chapter 2 on, which was called probability, right, introduced concept of calculating probabilities when you had equally likely events. Equally likely outcomes, really. Right? So if you have a certain outcome, certain event you're interested in, you can list out all the outcomes that are there, count the number of ways it can happen, divided by the total number of ways you can get some combination of things, some situation, and you get a probability. Right? There were some probability rules for things like union, intersection, complement, that type of stuff. Some of these things were expressed in Venn diagrams. Then getting past some equally likely outcomes, and we're actually dealing with that too. There were different counting rules, right? Counting the number of occurrences of ways of choosing certain numbers out of other things, or putting things in order, those type of counting rules. And that's largely what was in that second chapter. I don't plan to ask about that so-called Bose-Einstein equation. That was the one where it's with replacement, but it's kept in order. It was a little harder to count because you could have duplicates and triples and things and a little more complicated things. So it's basically counting things in order, with or without replacement, is most of it. There's that one add-on one that was a little more complicated to deal with, so we won't ask about that one. Although it comes up now and then. Right? 3 was on conditional probability. And so in this, you had to be told a number of probabilities for this to be possible, like a probability of an event A, a probability of another one given A, a probability of another one given that A did not happen. And out of those different things, you could make a tree, A and A complement, and then B and B complement could happen after that. And so you really have 4 outcomes: A and B, A and not B, not A and B, not A, not B. And that was a simple tree. The trees could be a little bit bigger than that. We had some things we did with that. Total probability. Say you wanted to calculate the probability of B. The probability of this one times that, plus the probability of this one times the probability of that one, and get the probability of the other events and other trees. Bayes rule for calculating, in this case, it'd be given that you're at one of these endpoints, what's the chance that you started in either the A or A complement group, so that inverse one. We did things with, we talked a little about odds ratios and things like that. I don't plan to put that on there. It's a good topic, and it's useful in many applications, but we have enough otherwise to look at. And then chapter 4 introduced discrete distributions. I'll write that on the next page. So this is kind of an outline of the major topics, right? A lot of it was applied, or in probability and counting. We did things like this story proof, that we'd have some equation and it would have the left side and the right side, and you wanted to show that these two things were equal. And sometimes you could do it with algebra, like manipulating the symbols and choose K and all that. Or you could do it numerically by showing it, right? There's also this story idea that sometimes you can explain how one story is counting something on one side, and how the other side is just another way of looking at counting the same thing. And we did that in a few examples, not a whole lot, but it was kind of a quick way sometimes to get some equivalencies between things. Maybe the algebra is a little more involved, right? So, but in any case, we will do a few of those. So it'll be, if it's asking one, it's going to be very similar, or even one we've seen before. So not a surprise. It's a little tricky to kind of formulate a few of those things on the fly. So in chapter 4, we looked at some discrete distributions, discrete random variables, and probability distributions. We have a kind of a general case where you could get values and then the probabilities that the random variable equals those values. So that might be given to you in numbers. We might take it from a table, like if you have a big table of counts, you might determine the probabilities from that table. Right? So there might be kind of a list of things. There might be a table of counts that you then convert to probabilities. You get 1,000 people, and there's the values, 1 through 5. Yeah.
I'm sorry, does that say curve? General?
General case.
Oh, okay, I'm sorry.
Kind of no. This pen sometimes is a little. I don't know. It's not like writing with a pencil, quite as easy. Right? Not that my handwriting's so good anyway. But, right. With these things, we calculated, expected values, the expected value of something squared, or in general, if, as the book expresses it, if we have some function of x, square root, cube, logs, anything we really wanted to do, any type of mathematical expression, we might take the expectation. And so it's a sum over all the values we can have of the function evaluated at those particular values, right, times the probabilities. So, and if it's linear, right, if y equals ax plus b, then we got that the expectation of y was just that function applied to the expectation. It worked out very nicely. We had a variance of random variables, which was usually we're computing as this version of things. But it describes the variability of the values that are likely. And if it's linear, right, then the variance of y is this a squared times the variance of x. So linear ones, you got squared. And then we looked at a few special cases. Bernoulli, so one trial with a probability p, or binomial with n trials and a probability of p. We looked at, there was geometric with a probability of p or negative binomial. And this was like having R geometrics. They're in there. We looked at Poisson, which counted things that occurred at a certain rate, 9 per hour or 4.5 per hour. That's primarily what we'll put on there. We did a little bit with moment generating functions. That we had some moment generating function. One thing we could do with this moment generating function is differentiate it and then set that argument t equal to 0. And that ended up being the expectation of x. There was another way to get at the moments, the expected value, or we could keep taking more derivatives to get the higher ones. But I don't plan to make it overly complex, but it was a useful thing to do. But that'd be about it. If you can do problems on those areas, similar to the ones that are on the practice, So the format of the exam is the exam, the questions will be written on the paper, and there'll be some space there to write the answers. And so I'll hand them out. If you have questions during the exam, you can raise your hand, ask questions, or sometimes it's just convenient to just step up here and then ask the question, right? And so it's gonna be written so, I think you would have time to do all of it. I wouldn't expect it to be a question of just totally running out of time. Now, that said, you don't want to go slowly, right, with anything. And so if you're really kind of unsure about a question, you think like you're spending a lot of time thinking about it, maybe answer some of the other parts first that go a little bit faster for you. Right? Now, I said that you could have 1 page of notes, right? So 1 page notes. So on that notes, you can write just about anything you want. You can type things up and print it. You can do formulas, probability formulas, examples, explanations for things. You can have sample problems you think are particularly useful, and so you can have things there that would be useful. And so for things like binomial, the expected value is n times p, and the variance is n times p times 1 minus p, and the standard deviation is the square root of that. And then the probability formula that you're equal some value is n choose x, p to the x, 1 minus p to the n minus x. So you can write all that down, or even a little bit more for binomial to have it there. You can do the other distributions. You can write some examples. Because we look at more distributions, than some of the intro classes, that is, it's a little bit more material to remember. But 1 page of notes, 1 side. So you do need to make some planning and deciding what you actually need on there. You can't reproduce the whole book. Not that it would help you so much if you have so much stuff to sort through. It's kind of hard to use it. But you could do that. Calculator. Some of the problems will have numbers. Be good to calculate those out to a degree. Show work. If you just type something in the calculator and it's wrong, and you give me just that number, there's no way I can give you any partial credit. Right? But if you write down a formula and then fill in some numbers for the n and p, for example, and then your calculation is slightly off, well, I'm seeing that you're understanding the problem and producing most of the work that we need, and there's just that detail there, right? But any questions? Yes?
Would you say that a lot of it will be like application and example problems, or will there be a lot of proofs that we've done in class and a lot of those?
So I think it's a little bit more applied.
Okay.
Some things with some binomial coefficients we've used a couple times to show things, and so it would be similar to what we've seen in class for part of that. So it's part of it, but more than half of it would be the applied examples, and I think that comes through in looking at some of the practice problems. So yeah, there were some review problems. I said I would start looking at this, exam 1 from there, and I think. Okay. All right. I'll go back over here and get it going. Okay, so we'll get this one open. So this is kind of what the exam looked like, right? So there's a page, right, and then there's some space to write in there. Right? And so this one started out on this one. It's a basketball player who makes 9 free throw attempts, has 70% chance of making a basket, and they're independent. What's the probability they make 7 baskets? So one challenge you have on the exam is figuring out what type of problem it is, right? Because there's all these distributions and other things that we've done. What does this one look like? set up like any of the random variables we've done. So a certain number, and these are the two numbers that are in there. It also says something about independence, right? So this is going to look like binomial. So the number of free throws is binomial in this case. There are 9 tries. Probability of 0.7 on each one. Right. And it's actually the probability that you, no, that doesn't move. Like that. The probability that you have 7 out of that number. Like out of 9. So then it's using the binomial probability formula to calculate it. So 9 choose 7, 0.7 to, no, yeah, 0.7 to 7, and then 1 minus that squared. 7 yes, and 2 no. The 9 choose 7, right, is the same as 9 choose 2. You either have to, out of the 9, determine the 2 that are missed, or the 7 that are made. This one's easier to compute. Right, 9 times 8 over 2 times 1 is 36. So it's 36 times 0.7 to the 7th times 0.3 squared. And if you type that in, you would get the solution. Right, for it. So, will this work? There's some solutions here. There we go. Hey. But it kept the, so that's written there. Everything's written on top of it. Great. So it ends up being about 27%. That play would make 7 out of 9. Right? If it's at least 7, you're going to have to calculate the probability of 7 plus the probability of 8 plus the probability of 9 and add those together. So it could combine probability rules a little bit. Right? Most of these are going to be kind of, if I actually do the probabilities, I'm not going to say, you know, what's the chance of 80 or more out of 100 to make you calculate 80 through 100. You know, not that good of an evaluation to do that, right? But any questions on this one? That's kind of a mess between these. So that was so make 7 free throw attempts with a 70% chance, and each is independent of others. What's the distribution of the number of an additional 7? So in the course that we did last year, there was a little bit more emphasis on adding together binomials and showing that if you add 2 independent binomials together, you get another binomial. So that this one wouldn't be as, you know, exactly, we didn't do all that much like that. However, you do know that a binomial is a sum of Bernoullis. Right? So 0, 1 trials, and if you have 7 of them, right, and then you take another 7, and they're all independent, the same probabilities, well, you're adding together 14 of them, right? And so that should be another binomial. Right? There's kind of more formal ways with convolution to show that, but that's actually what, yeah. Another way to ask that question, so as a binomial question, if you have 1 that's 7 attempts, 9 attempts, is that what it was? Oops. Back over here. 9 attempts and another 7. So the first one is like this. So that's maybe x, and then y is a binomial with 7 attempts at 0.7. Right? Y is the sum. X plus y. A random variable that's a binomial with 16 trials and probability of 0.7. Well, you know, if x is all 9 Bernoullis added together and y is 7 more Bernoullis added together, and the total is just all those added together, that's the story behind a binomial. That's why it works. Alternatively, if these two things are independent, the moment generating function of the sum of 2 random variables is the moment generating function of one times the moment generating function of the other. And if I told you that the moment generating function of a binomial was p e to the t plus 1 minus p raised to the n power, so the 9th power for this one. And this one was p e to the t plus 1 minus p raised to the 7th power for the second one. And those two things, you can combine them and get a moment generating function, p to the t plus 1 minus p to the 16th. And the values of x plus y, you can get 0, 1, 2, right, all the way up to 16. And so it has the range, it has the moment generating function for a binomial 16. 16 with some p, in this case p is 0.7. So if I gave you the moment generating function, you could kind of more formally show that. But most of the problems would be more applied. But any questions about? How about the second one? All right, so the second one, the field hockey team has an A squad and a B squad. Each have 14 players. There's a goalie, right? And then 10 field players are picked randomly from the field players of the combined squad. So what's the probability that 8 are selected from that A1? So this was one of these counting ones, right? How many ways are there to select the 10 players altogether? Yes.
10 choose 28.
Or 28 choose 10, yeah. Right. So yeah, express that way, right? So there's 28,
Yeah.
choose 10, the other way around to get the right numbers, but yeah, express that way, right? So now if you want to divide it into these two groups, right? There's 14 in each. And we need to pick some from the first. We need to pick 8 from A. That's what it says, right? And 14, we need 2 from that. So that would be the numerical kind of solution there, right? So it's kind of similar to the capture-recapture problems that we did. You know, you had one group and then a tagged group, and you're picking some new ones, and there's some that are tagged and some that aren't. And kind of that same representation as the issue. Right? Part B, what's the probability that in addition to the 8 field players being from A, there's also a goalie picked from A? And so this one, it can be a little fuzzy in terms of exactly how it was interpreted. Is the goalie one of the 10, or kind of the thought was that there'd be one more pick, right? And so after you pick this, you need to pick a goalie. So maybe you need to pick 11 people. And overall, right, 10 plus 11. And there are 9 that are picked from that one, but one of those people has to be a goalie, right? So there's a 9 coming from here, and so one of those has to be a goalie, so it's just a little bit more to describe the problem. And the answer to this one last, different students interpreted it different ways. I thought, you pick a goalie, and then you pick from what's left, or maybe there's another group of goalies out there, so you pick from those, and then you pick the field players and things like that. So, but some fashion of dividing up the counting into a series of steps. And so, you can calculate those on your calculator or simplify them and write them out. That would kind of be the final answer. In terms of time usage on the exam, if you write this out as a formula, and feel like you need to move through some other questions, you could leave it like that, and then come back to it if you have time towards the end, and then fill in the exact numbers, but at least give the formula for how you're thinking about it. If you want to explain what these things mean, you might, you could put little notes saying that, this is select from B. And so it shows a little bit more of your logic of how you're thinking about it. You know, if you nail it, get the right things exactly, and I understand what you're doing, that's great. If you add a little more details, then it can help me understand how you're thinking about it. So, yes?
If we get to this step, can we use our calculator after this, or do you want us to like show out?
Yeah, you can use the calculator to do that. If, like this one, you know, it's the same as 14 choose 5. So, you know, for some of them, it's almost faster to do it by hand, like the 14 choose 2 is just about as fast doing it with your calculator or writing out the numbers. But either one is fine. You have your calculator, you can calculate these numbers. But I would suggest writing these down before putting in the numbers, just so you get that as a possible way to get points as well. Okay? I realize that there's a possible way to save this, and sometimes it works and sometimes it doesn't, but it's on the video. Right? So here's another third question. An alpine skier has a 70% chance of improving her time when the wind on the mountain has a low velocity. The skier has a 40% chance of improving when the wind has a medium velocity, or 20 when it's high velocity. Right? On the mountain, the wind is low 30% of the time, medium 50, or high 20% of the time. And so what is the probability that the alpine skier improves her time? So what type of problem does this look like?
Let's draw a tree.
Let's draw a tree, yeah. Yeah, when it's that many probability things set out, it's very likely a tree of some sort. Right? So there's the wind levels, you know, low, medium, and high. Low, medium, and high, maybe I put them over here. And the chances we go down those paths, low is 30%, medium is 50%, 20%, like that. And there's improvement, 40%, or 70%, sorry, up here with low velocity, 40%, and if high velocity wind, it's only 20%. Right? And so that the negative that does not improve is 1 minus that. For those, so this is improve, right, and no improved, improve, and no improved. So the chance for improvement, right, what is that? Multiply down the rows, down the branches till you get to the endpoints here that have improvement. Right, so there's 3 of them with improvement. So 0.3 times 0.7 plus 0.5 times 0.4 plus 0.2 times 0.2. So it's 0.21 plus 0.20 plus 0.04. So it's about 0.445. So there was 70, 40, and 20, and 0.45 is somewhere in the middle of those 3 rates of improvement, kind of weighted by the chances. So what's the chance that the skier does not improve? 1 minus that, right? So sometimes the question will ask one way and then ask for the opposite, and sometimes you can avoid having to redo a longer calculation by taking the opposite to get the shorter one. So this is the probability of improvement, and this is the probability of not improvement is 1 minus that. Often I follow these up with a Bayes type question. The skier improved. My time got better. Oh, what was the wind like today up on the mountain? Is the question. Right? So the skier improves. What is the probability that the wind was at low velocity? Go the other way. So that Bayes one. So the skier has improved. What's the chance that it's low velocity? If you like doing things with A and B's and just using those letters, that's fine. You can use words. You can use more trees to base it off of. I like to do it with things that are related to the problem. So there was how much wind, for. So in Bayes, there's a chance that it's low and the chance that it's improving if it's low, right? Over the chance that the skier improves. Well, the chance was 0.45 for improvement. The chance of low wind was 30%, and improvement given low wind was 0.7. So it's a 0.21 over 0.45. So 21 over 4.5. So that's both of those divisible by 3. So that's 7/15. So a little less than 1/2. 0.47 calculated. A little higher than 30%. 30% of the time the wind was low, generally, but if you know that the skier improved, that's associated with better chance of improving, so that probably goes up. Any questions about? Yeah.
I've never really understood what the bar in the middle of the.
Yeah, so it's kind of just a dividing bar, and the thing we're asking about the probabilities of these things, and the things to the right are the things that were given or known. So it's like, these are the facts we know. So the skier comes in and says, I improved. And now you're wondering, oh, what was the wind like? And so we're asking about the probabilities of things on this side, and this is what we're given or conditioned on. It's kind of like having a denominator. Like you ask what's the chance of diabetes, and then you're told that somebody has a body mass index over 40, which is quite large, right? Then you're asked, then the body mass index greater than 40 would be on that side, right? And you're asking what's the chance of diabetes among somebody that's like that. And so it's kind of just telling you what the denominator is or what group you're basing it out of, and then. So in this case, in the picture, right, given that the person improved, we know that, which one it shows up on this one. Right? Given the person has improved, we know that we're in one of these 3 endpoints. And now what's the probability we're in this one out of those 3? So what's that?
So that's why on the, could you go back to the others?
Yep, yeah.
So over on the other side of the equals where it has,
Yep.
So that's why it's 0.7.
Yeah, that's why this is the conditional one here. There's 30% were low. That given that you know it's improved, that thing's in the denominator. So there's a 45% chance of improvement. And now what's the probability out of that? What fraction of that goes to the low side, the low wind? Good. Wipe that out again. So that one, here's one, it's kind of a Venn diagram. 40% have taken calculus, 70% have taken intro statistics, and 20% have taken neither one. 4% have taken at least one of these 2 courses. So at least one, so if there's calculus, it's a C, and statistics is an S. Right. There's division here, calculus or statistics, and some people have taken neither. Neither is outside of here. It's outside of those 2 boxes. 0.25. Right. This would be both inside. At least one is either one or both. So that would be the C union test. Both inside here is the intersection test. Right? So that's that one. And so one formula that we have, right, is that the probability of either one can be calculated as the probability of one plus the probability of other, minus the intersection. We are given 40% for calculus, 70% for statistics. Now, we're not directly given either of those other things, but what's the opposite of neither? neither one, so it could be either one, right? So it can be C or S, right? So neither is not C and not S. That's outside of both of them. That's 1 minus C union S. So either one. So if 25% have taken neither, 75% have taken at least one. Right? So this one's 0.75, and then we just have this one thing that's unknown. I guess this is the answer really to this one. Right? And then this is 0.1 minus that would be the answer to this other one. Sometimes it gets a little bit more complicated. So you know somebody's taken statistics. What's the chance they've also taken calculus? So you can do a conditional probability in this case. So the chance of both, right? It's 0.1 minus this, 1.1 minus 0.75. So there is 0.35. I've done both. Then if you ask, what's the chance, so somebody's taken statistics, what's the chance they've also taken calculus? Right? Writing that as a conditional, so someone is taking statistics. What is the probability that the person has also taken calculus? So also calculus, and then I would write the statistics on this side, okay? To the left of the line, meaning that's what we've known. We know that about the person. Now we're asking also calculus. Also calculus, if they've taken statistics, really means they've taken both. Right? So C intersection S, given statistics, is the chance that they've taken both over the chance that they do this. You know, we would say taking the intersection of these things, but it's just redundant. So it doesn't really change. The C intersection S is smaller than that. Right? So this was 0.35, and the statistics I think was 0.7. And so it'd be 50%. There, kind of taking that question and asking it a little bit different way. So work with those, try to express things in different ways if it's a question like that. So as right. Any questions about it? Yes?
Yeah, I'm sorry. So we found the probability of the intersection as 0.35?
Yes.
But then we said that the thing we just calculated is essentially the probability that they've taken both. So wouldn't the probabilities be the same?
So if if it's probability of both, but divided by the chance that they've taken statistics, right? Because it's conditional. It's asking also that they've taken that, given that they've chosen statistics. So we're in this set of individuals that have taken statistics. So
Like the order they've taken it?
well, it's not necessarily the order, but we know that they've taken statistics, and they ask you, did you also take calculus?
Okay.
And so instead of just having the numerator, we have to divide by this the other thing that we're given. Right? So that makes it different, right? 0.35 to 0.7, and it's a little bit higher.
Can you kind of explain that in terms of like the Venn diagram? So that's like within the statistic like bubble,
Right.
about what you're saying about half of the people.
Yeah, so this is all of statistics, right? So we had 70% that are over here. Well, what percent of those are both?
Okay.
So both is 35%. So if we filled in numbers in those bubbles, there's 35 that are both, there's also 35% that are
Okay,
statistics.
yes, I see.
And so it's half and half. Calculus was 40%, so there's 5% here. And then 25% outside. So that's 70, 75, that adds up to 100% altogether. Maybe I'll look at, maybe this, it comes up whether I have the solutions there or not. So, I just erase these things. If I did it just quick. So, suppose you make words by randomly sampling letters, it's kind of like the driver's license with numbers, but now with letters. So a no repeat word, a string of letters that does not contain the same letter twice. Right, like cat is no repeat word, right? But something that would have the same, so like cell or ball has repeating letters. Right? And order matters for letters in a word. What's the probability that you randomly generate a word of length 4, so 4 number, that is a no repeat word? Not necessarily that it makes sense, but just that it's a string of letters. So if we're generating 4 letters, how many ways can we generate words of length 4? Any 4 letters together is called a word.
26 choose 4.
26 choose 4. Well, so 26 choose 4 is, I think, would be a common, answer for something like this, right? So that's certainly a way of picking 4 different letters out of 26. Right? But, yes?
Is it 4 factorial?
Yeah, there's a 4 factorial would be a way of, if you had letters, say you, A, B, C, D, how many ways can I put those in this pattern? I can put, 4 choices here, 3 choices here, and so on. So if we're doing it without replacement, it's going to be going down like that. Right. This one, this combination though, was used if it's unordered. Right? So it doesn't matter what order, but this words, we are keeping them in order. Right? So when things like this, right, it's 26 choices for the first one, 25 for the next one, 24, and then 23. Right? Ways of picking 4 letters without replacement and keeping them in order. So it's 26 times 25 times 24 times 23. Right? But if you get to reuse letters, right, then it's just 26 to the 4th, because you get 26 for each of those choices. And so that'll be the probability. There's a pretty good chance you get a no repeat word, because there's 26 letters. We haven't used that many of them with 4. So this does answer another question, right? What's the chance of choosing 4 letters, but not keeping track of their order? Right? What's the chance that you do? Yes.
So is that divided by 26?
Yep.
Okay.
Yeah.
Why is that?
So this is, we want a probability, right? Then we're going to count the number of ways we can make one of these words, and it'd be no repeat, right? So that's 26 times 25 times 24 times 23. But the total number of words, if you allowed repetitions, like A would be allowed under that.
Right.
Then there's 26 choices for the first, 26 for the second, 23rd, 26 and 26. So.
Yeah, I just thought the problem said no repeating.
Right, so this is the denominator. So this is all possibilities. And this one is number of no repeat. So the probability of a no repeat is the number of ways you can get a no repeat over the total possibilities. The other ways have some type of repeat. Yeah.
Is the numerator technically the permutation formula?
It's called a permutation of so 26 items and choosing 4. I mean, but keeping them in order. So it's technically what's called a permutation.
Okay.
Yeah.
Now, say you added like, so that was the first word, and then you do a second word of two.
Okay.
Like, or two choices, and then you can repeat the same letters. How would you go about that? Would it
So-
just be that times 26 times 25 over 26 to the fourth?
Yes.
Okay.
So if you say that now we're going to do another word, it only has 2 letters, what's the chance that that one also is a no repeat? Right. But you get to start with all 26 again. You don't care if there's repeat between the 4 and the 2. Right. Then it would be, yeah, the first 2, 26 times 25 over 26 squared for that word. So you have a series of them.
Or yeah, squared enough.
Yeah. Right, so this is, so here's a story problem type of thing. So no repeat words, right, can be 1 letter long, 2 letters long, 3 letters long, up to 26 letters long, right? After 26, there's no more letters, so you gotta repeat one, right? So how many no repeat words are there if you allow the lengths 1 through 26? So why are these 2 formulas the same? I have a story way, there's an algebra way too, right? So if you want to do an algebra way, with formulas.
I mean, you could break apart the choose and just go about that algebraically.
Yeah. So this thing is n factorial k factorial over n minus k factorial. That's one definition of that thing. You have your k factorial here. So the k factorials can cancel. But what's n factorial over that one? At some point, you get a lot of cancellation. Right? You cancel all the n minus k factorial terms out of that. So what you're left with in the numerator is n minus 1, n minus 2, down to right, n minus k plus 1. Because the n minus k minus 1, everything else is gone there. Right? And so if this is the same inside of here, and if it's the same over there, and the summations are the same, these things are the same numbers. So this one, algebraically, is not so difficult to show, right? If you chose small numbers, say you choose something like n equals 3, right? Then k can go 1, 2, or 3, so you'd have 3 terms on this side and 3 terms on this side. So if you actually put the numbers in, you could see that they came out the same kind of numerical example. But in terms of stories, right, does anybody want to try to? How do you choose no repeat words? Right. Well, they have somewhere between 1 and 26 letters in them. Right? So they have k letters, or n letters, right? Or I'm sorry, k spaces that you're going to fill in. Right? For the first one, you can choose any of them. You can choose all 26. For the next one, you can choose 25, and then 24, down to you filled in your word of like k, right? So we took 26, 25, 24, 23 for 4. But in general, it goes down to you got enough. Right? So that would be all the, add all those up over all the different lengths, that should be the number of words. Right? This one, right, it says choose k letters out of n. Right? And then put them in order. The k factorial ways of putting them in order. So it's also picking k distinct letters, but that's without respect to order. We think the words are different depending if it's which comes first and which comes second and so on. So this one means put them in order. So something like that, right, could explain that more with a story connected to the words. Right? But there's an algebra variation too for explaining that. So I'm more inclined to give you kind of an option, do an algebra version or the story version, or maybe numerical version, depending on what it is. Right? But it's kind of showing that the left-hand side somehow is the same as the right-hand side of some of these equations. Any questions? So, this one, well, that was all that was on that one. This one didn't, I don't think it took quite as the full time. No, we were on, maybe we were Monday, Wednesday, Friday, so it was a little bit shorter. The thing that would be, that was not covered at that point in this one was kind of computing an expected value. You know, moment generating function type of thing. There's nothing on that one on Poisson distribution primarily. So there's a few things that, you know, so there might, to go from the 1 hour class to about an hour and a half, there might be another problem on one of those other topics. Right? That's where some of the other study guides come in. That there are some other problems on those related to the other topics. But before we go into that, are there any topics you particularly want to ask questions about or homework? Yeah.
Can we go over the linear transformation?
Uh-huh. Yeah. So let's do that in the context of one, you know, like, let's see. Let's look at one practice again to kind of give an example. So this one that's called the review problems. The first one that's here, review problems 1. This has some sort of table, which is a little bit different for getting proportions. So here's a question. So this is compacted so that I can put it on the review sheet and not take as much paper, but this would probably be stretched over a page or two so you could write answers in there, right? So here's a probability distribution of the number of living plants in meeting and conference rooms of 2 large hotel chains. Right? Chain 1, chain 2. Here's probability. Here's the number of living plants, 0, 1, or 2. What's the expected number of living plants for each hotel chain? And how do they compare? So given this information, how do you compute the expected values? The expected number of plants? Yeah.
The sum of the probabilities times the number of plants.
Yeah, so 0 times 0.15, 1 times this, 2 times that, right? And so, I think I'll go to so 0, 1, and 2 are chain 1 and chain 2. The probabilities there are 0.15, 0.50, 0.35, 0.40, 0.40, and 0.2 as the probability to change. So the expected value of the number of plants here, 0 times 0.15 plus 1 times 0.5 plus 2 plus 0.35, so 0, 0.5, 0.7, so 1.2 plants in this conference center. And this one had on average 0 times 0.4 plus 1 times 0.4 plus 2 times 0.2, so it's 0, 0.4, 0.4, 0.8 plants on average. Not a lot of plants. So say it costs, maintenance of a room costs $500 plus $50 per plant. They got to do some maintenance anyway. They got to vacuum it, dust it, clean it up, and that's some fixed costs they have to do on each room. But if there's a plant, they also have to water it and clean up the leaves, and it takes just a little bit longer. Right? So what's the expected cost per room for a hotel chain in terms of maintenance? Well, since this is a linear transformation, the expected cost is, we can put in the expected number of plants in there and get the average value. So this is 500 plus 50 for the hotel 1, which is 1.2, and it's going to be $560. Whereas the second hotel chain didn't have as many plants, its average was 0.8, so that's $540. Maybe the first hotel has to spend a little bit more, but maybe it's considered more fancy and it's, nicer impression and things like that. Gets a little better business. Not the plants would be the whole thing that would determine it. It could be part of it. Having artwork on the walls and so on. What's the variance and standard deviation of the number of plants? That's the other type of question that could come out of it. To get the variance, we'll take the expectation of x squared. So expectation of x squared, there's 0 times 0.15, 0 squared, plus 1 squared times 0.5, plus 2 squared times 0.35, so 0 plus 0.5, plus 4, 140. 1.9 is the expected x squared, so the variance of x is that number minus the average number of plants. 1.44, so it's 0.46. So the standard deviation of x is the square root of that. It's about 0.7. 0.49 would be 0.7. It's kind of close to 0.7. Let's just use 0.7 for convenience, right? So that's the standard deviation of the number of plants. Not every room has plants. There's variability, 0, 1, 2. So there's variability in the cost because the cost depends on the number of plants. So the standard deviation of the cost, again, the equation was 500 plus 50 times x. There's this multiplier of 50. So it works as 50 times 0.7. So there's a standard deviation of about $35 per room. Somewhere for this one was the 560 average, plus or minus about $35, depending on the presence of plants. So this is the application of the linear transformation and how it impacts the standard deviation. This is these formulas are shortcuts, right? So if you did explicitly take the 0, 1, 2 plants, is the number of plants, and then you did cost. This one's going to cost 500. This one's going to cost 550 because that's one plant. This one's going to cost 600. And so these are the probabilities here. So you can do the expected value of cost as the cost in one of these type of rooms, 15% plus 550 times this plus 600 times this one. And you're still going to get the 560 as the cost. Right? If you imagine taking, right, yeah. So you could convert the data, the numbers, to the costs, and then average those with the same proportion, then you get the same thing. But because it's linear, if you've done it on the plant scale, right, you can do the quick conversion. Right, 500 plus 50 times the average of the plants. Right. So it's giving you the same thing, but it's just a kind of a shortcut. But there's some more questions there to do. And so one suggestion we're studying is look over the past homeworks, 1 through 5. I'll post some homework solutions for this homework 5 quickly. I guess I'll try to have it, graded pretty quickly too. Right? So if I can get it, I don't know if I can get it graded by tomorrow morning, but I can probably get it graded before my first class. So maybe tomorrow afternoon you can get your paper back. I'll have to leave them outside of my office. Right? So I'm in John Marie 259. There's some mailboxes that are next to my office. I can put them in a folder in there, and so you could go by and get your particular folder. Yeah.
Can you do the last one on the homework due today?
The last one that was on homework due today. Yeah, let's take a look at that. Was that moment generating function one?
Yeah.
Yeah. So, right. So the moment generating function type of problem. If you have a moment generating function, for negative binomial, it's this 1 minus e to the r. And then, p is a probability between 0 and 1. Q is 1 minus that. So p is also 1 minus q, p plus q, these are the 1. A couple identities related to that. When things involve p and 1 minus p, a lot of books will substitute that q in there just to make it a little less cumbersome. So we're going to take to get a mean of the random variable, we're going to take the derivative of this stuff, right? So one way of writing this is p to the r, 1 minus q e to the t to the negative r. Putting like that might make it a little bit easier to keep track of things. And so you take the derivative with respect to t. That's a derivative with respect to t up here, right? So p to the r is just a number. It doesn't involve t. And then this is something to the power. So you can take that power outside, 1 minus q e to the t, and then the power goes down by 1. And then you take the derivative of what's inside. So negative q e to the t. All right, so there's a couple of negatives in there. Get rid of those. I'll pull an r out front. And then there's 1 minus q e to the t. Negative. Now, this negative r minus 1 can be written as negative of r plus 1. And then there's a q e to the t. So to get the mean is you can fill in t equals 0. And so e to the 0 is going to be 1. So effectively, that's going to kind of wipe out the e to the t's. So you end up with r, p to the r, 1 minus q times 1. And there's negative r plus 1. And then q. But 1 minus q is p. And so you have r, p to the r over p to the r plus 1 times q. Right? So there's one more copy of p down below, so it's r times q over p, or expressed in terms of only p minus p over p, right? So that's the mean of a negative binomial. Any questions or not? There's, I haven't, I've gone through this a few times. I don't know how many times. But anyway, kind of dealing with the exponents, it's a little bit easier if it does that way. And so it's just kind of getting used to it. It's a little messy, admittedly, dealing with these things, but it works out. If you needed the variance, you'd have to take the second derivative of this thing, and the second derivative, there's a p to the r, r cubed that you can pull out. So here, there's a p, there's r, p to the r, and a q. Those things don't involve t, so I can pull them to the front. And then it's the product rule, because we got something with e to the t and something else times e to the t. So the product rule, if you take the first one there's this 1 minus q e to the t, and then there's this negative r plus 1. The derivative of the next piece is just e to the t. The second one there's an e to the t, and we're taking a derivative of the first one. So it's a negative of r plus 1 times 1 minus q e to the t, negative r minus 2 up there, q. And so it's negative r minus 1, right? That's negative of r plus 1. So you get that exponent, out front, and then you take it minus 1 more up there.
Negative QE to the T?
Is there a negative q e to the t?
If it's the derivative of what's inside the inner Q.
Yeah, it should be a negative in there. Right. Is that right? Negative q. Yeah, I guess. So there's p to the r q. Doing this thing, what we want to do now is put 0 in for t. So it's p to the r times q. And so there's 1 minus q to negative r plus 1, and then an e to the t guy goes away as 1, plus that negative, as you mentioned, is important because it gets rid of that one. So there's a r plus 1 e to the t. Oh, the e to the t's go away, sorry. E to 0. And then 1 minus q to negative r plus 2 up here in a q. And that's p, right? So then we p to the r times q. But we can pull out p to the r plus 1. How did I get that? 1 minus q is p, and there's a negative r plus 1, and there's 1 extra over here. So it leaves 1 plus r plus 1 times q over p. Something like that.
Yeah, the P needs to be the R plus 2.
P to the, there's an r plus 2, but I pulled some of those, r plus 1 of them out here. So q over p. Yeah, so if you do it carefully, and then take the, sorry to kind of wave hands here at the end, but I feel that our time is kind of getting, and then take the squared one minus the square of that first one, that gives you the variance. And that should come out to the formula that's appropriate for that one. So keeping it all straight and doing it all neat and careful. That's a more complicated than I probably asked on that, because the negatives and the change rules kind of messy. But you get some experience of what it can be like, right? So how did we get that formula anyway? Right? What is the definition of moment generating function? Right? So it's an expectation. Right? Again, you can put this down on your formula sheet, right? It's the expectation of e to the t x for the random variable. So for a discrete random variable expectation, we always take a sum over the probabilities times something. So the sum over all our values. This is a negative binomial. So x can go from 0 to infinity. And the thing that we put in here as the function is e to the tx. And then the negative binomial probability. Right? So there's r successes. So there's always 1 minus p to the r. And then there's 1 minus p to the x failures until we get our r1. So there's that probability. And then there's a combination thing here. So we had r successes and x failures. The last one has to be a success. Because we stop once we get that. So there's r plus x total minus 1, because the last one isn't really free. And then we have to put in that r minus 1 times, we have to put r minus 1 of the, or in the, we put r minus 1 of the successes back in that first group. And then the last success happens. So that's what they did, right? And then you have to manipulate that to get the simplified formula. But we didn't go through that one so much, but some of the others use binomial expansion or different versions. But more will be applied, like taking derivatives to find a mean. And the other.
So the et to the x gets plugged in for x in these formulas, or just gets multiplied by?
So in expectation of anything, right, so x is the random variable. And so whatever function we have in here, so the expectation of some function of x, if x is a length, if you want to square it to get area, or it's pi r squared, pi x squared to get, area of a random circle. Maybe you're harvesting trees and you have you want the area of the tree, and then it'd be pi r squared. Whatever that function is, that gets put in here, and then you put the probability for that x outcome over there, right? So in another context, I don't know, that it's the volumes of tree in any case, so that's kind of what you would do. So the expectation of something like x to the 4th, we would write it as the sum of x to the 4th times the probability that x equals x, or whatever distribution you're using. Or if it was expectation of x minus the mean to the 4, kind of the centralized 4th one associated with how heavy the tails are of the distribution, how spread out the extremes, then that says take x minus mu to the 4th times the probabilities that you have those values. So as the function changes, the thing that goes in there, right? So the capital X over here, these are capital X's as random variables, right? So it represents the idea that there's possible values and then different probabilities for them. And this is the sum over the actual values that we can actually have, because we can actually put numbers in here and try to make it consistent between these squiggly X's and so on. I had one professor in graduate school who was would just had impeccable handwriting, could do everything like that with X. He actually did X's with like an extra little kind of funny loop thing down there. So it was in any case, try to distinguish between values and then this concept of a random variable that really kind of describes the process of measuring. You're going to have values, they have different probabilities, so different chances. Yeah.
Can you do 3 as well? That'll work. I think it's sort of building off this.
Yeah, so what was 3 off of that? Oh, yeah. Yeah, so with a Poisson random variable with some parameter lambda there, that, so it's actually this. What is the expectation of e to the 3x? Maybe for some reason you're interested in that function. I don't know why exactly, but you're interested in it. Right? So what we've been just saying with the definition of expectation is you would add over all the values of that function times the probabilities that you would have each of these outcomes. So there's a lambda to the x, e to the negative lambda over x factorial. Right? And so these Poissons are giving these probabilities for us in there. Can we simplify that? Well, the moment generating function is e to the tx, right? Where t is kind of a placeholder. Right? When we take the derivatives, we set t equal to 0. But you could let t equal anything else you want in there. And so if we know that this expectation of e to the tx, this thing, is e to the lambda e to the t minus 1, we know that that is what that equals. Right? What we're really asking is what's the moment generating function equal to when t is 3? Right, so if we let t equal 3, the moment generating function at 3 is the expectation of e to the 3x. Right? I didn't tell you what lambda is, so that's still kind of this arbitrary parameter. It's the rate that something's happening in the Poisson process. But you can just put 3 in for t in this formula, and so it should be e to the lambda e cubed minus 1. That should be the expected value. Kind of a funny formula. I don't know what exactly we use it for, but that's kind of plugging in a value there. So this value of t in the moment generating function, like where does that come from? I mean, it's kind of a placeholder for use in a Taylor series expansion. And that's where the moments pop off of the coefficients on those. So there's a rationale for doing that. But t, you could plug in these other values, and then you get this extra thing out of that. One distribution where that's very useful actually is something called log normal. So if something is very, very skewed, like revenue and of certain companies or returns that can be very high, or low, the log of that might look like a kind of a normal distribution. And so the inverse of that log of a distribution is e to a power. So there's some use for actually using this e to a power for things in log normal distributions, going back and forth. But anyway, that you're just plugging in would be one solution. The second part was asking, okay, starting with this, show that you actually do get this thing, right? Kind of going back to the argument that we used to say, what is the Poisson moment generating function? Well, how did you do this? Well, this thing over the values, there's an e to the 3x and lambda to the x. Now first you can pull the e to the negative lambda out, over here, outside of the picture here. So that it's outside of that. There's an x factorial here. But you can actually combine these two things, right? Lambda, e to the 3, all of that to the x power. And this goes from 0 to infinity. That's how you can combine those two things with that same exponent. And this, with special summation, is e to the lambda e cubed. Right? It's e to the thing that's inside. And e to the negative lambda. So if you combine those things, you get e to the lambda e to the 3 minus 1. Maybe, I think I forgot a bracket. Sorry about that. I must have forgot a bracket. Right. And so that's the few steps that kind of go from definition of expectation to simplifying it a little bit and then getting this form. So if you knew the moment generating function was this, well, that's just asking me to put t equal 3 in there and getting that quickly. So kind of two ways of trying to help understand a little bit that moment generating function. So good questions, good pair of questions. Expectation and moment generating kind of go together. And linear combinations. Nice combinations. But, so then I guess the final suggestion is, study things, make up a sheet with formulas and things like that, and then look back at some of these study problems. See, based on your sheet, you recognize what type of problem it is, what type of words or things would key you in that it's a certain type of problem. Right? It's somewhat quite different than others. Right? Some will specifically say Poisson or binomial or something, and then others will just have to give you all those probabilities for like the trees and stuff. Right? So this kind of phrasing that you would pick up on, and then try it like as if it's a test, right? If you, the night before, just read through the answers and say that looks pretty good, it probably will help, but it probably won't help as much as if you really kind of test yourself. Right? And there's a few versions, so they're a little bit different in their emphasis and over time, but between them they give you some homework problems and solutions worth studying. Okay. But I'll have my regular office hours, Friday, Monday, which is always budgeting. And if you have homework 5, I'll pick that up. Number 3. I said I'd like
Sid, are you Italia?
Sure, yeah.
Sorry, I didn't see that.
Sure, I can take that one, and then you can bring it by. And yeah, if I'm not there for some reason, just drop it off. I'll be here for another hour or so.
Okay.
So you can just drop it right under the door.
Okay. Thank you.
Yeah. Thanks. Thanks for your question.
Yeah.
Tom.
Good, how are you? Right.
Thank you.
Is your last name Kruger?
Yes.
Yeah. Great.